So now, having looked at ionic bonding, the next unit we will look at is molecules and covalent bonds. So these are the learning objectives for the unit. You are to know what a covalent bond is, also in terms of electrostatic attractions. Understand how to use dot-cross diagrams, this time to represent covalent bonds in the following types of molecules. Explain why substances with simple molecular structure have low melting points or boiling points, and we'll use the term intermolecular forces to explain that, and explain why melting and boiling points of simple molecules increase as their masses increase. Explain why substances with giant covalent structures are solid with high melting points and boiling points. Explain how the structures of carbon allotropes influence their physical properties, so we'll look at the term allotropes. And finally, you'll have to know that covalent bonds do not conduct electricity, and possibly the reason why. So, covalent bonding. So here we have the covalent bonding between two hydrogen atoms. So what's happening? Well, ionic bonding, which we've just looked at, involves a non-metal taking electrons from a metal. Covalent bonding is a little bit different. In covalent bonding, this involves a non-metal sharing electrons with another non-metal atom. So in a covalent bond, this results in electrostatic attractions, just like an ionic bonding, but this time, rather than the electrostatic attraction being between different ions, it is now between the positive nuclei, because remember, that's where the positive protons are contained, and the pairs of negative electrons that are being now shared between the atoms. So covalently bonded substances actually fall into two distinct types. The first one are the simple molecules, just like the hydrogen molecule here in the animation, and giant covalent structures, which we'll look at in more detail later on in the lesson. So these simple molecules contain only a few elements, 1, 2, possibly 3, held together by these strong covalent bonds. And the example provided by the animation is hydrogen, which is a molecule which contains two atoms of hydrogen which are bonded together covalently by sharing their single electron to form a covalent bond.
In this video, we are going to learn about the octet rule and how to construct dot and cross diagrams to show the covalent bonding in hydrogen, oxygen and nitrogen. As seen in the video how atoms bond, when two hydrogen atoms bond, the shells overlap, and because each atom only has one electron to share, there are two electrons being shared over two shells. These are represented by a dot and a cross. Which noble gas does this correspond with? Pause the video and continue when ready. The answer is helium, which has two electrons in its outer shell. As a result of electron sharing, each hydrogen atom now also has two electrons in its outer shell. In the next example, we are going to consider oxygen. It's in group 6. Therefore, how many electrons does each oxygen atom need in its outer shell to fulfill a noble gas structure? Remember, oxygen has 8 electrons in total, so we would need to fill the second shell. Pause the video and continue when you're ready. The answer is that each oxygen atom needs 2 more electrons before fulfilling a noble gas structure. This is also called the octet rule. In this example, the octet rule is fulfilled because each oxygen atom shares 2 electrons in the outer shell, forming an O2 molecule. If you count the number of electrons in each shell, you should notice that each shell has 8 electrons shared over 2 shells, shown by the dots for one oxygen atom and crosses for the other, which is the ideal. Whenever you draw a dot and cross diagram, wherever possible, you should ensure that A, the electrons are equally spaced, and B, that they are paired. The fact there are 2 shared pairs of electrons in the middle where the shells overlap means that the oxygen molecule O2 has two covalent bonds connecting each oxygen atom. This is called a double bond. Each of the nitrogen atoms has 5 electrons in their outer shells. How many electrons, therefore, do you think each will need to share to fulfill the octet rule? Pause the video and continue when ready. If you said that 3 electrons are available to form a shared pair, you'd be correct. You should see that there are 3 shared pairs of electrons in the overlap of the shells. This is called a triple bond. You should also notice that this example fulfills the octet rule.
So just like in ionic bonding, you can use dot cross diagrams in covalent bonding or to show covalent bonding. So the diagrams show how the electrons are now being shared between the atoms in a molecule. The crosses represent valence electrons or outer electrons for one atom, and the dots represent the valence electrons or outer electrons for the other atom. And you don't have to worry about the other electron shells, just the outer or valence electron shells. So that saves a bit of time when you're drawing them. So let's look at an example of hydrogen fluoride. Okay, so you can see from the dot cross diagram that the hydrogen is sharing a single electron represented by this cross with the fluorine atom, which is also sharing a single electron. Okay, so that means that hydrogen has 2 outer electrons in its valence shell, so it's happy, it's nice and stable, and the fluorine is also sharing 1, 2, 3, 4, 5, 6, and 8. Okay, so it's got 8 electrons in its outer shell. By sharing that 1 electron, it also gets a full valence electron shell, so it's also happy. So how do you draw dot cross diagrams? Well, the first thing you do is you draw the outer shell of the atom with the lowest group number with electrons as a pair of dots. The unpaired electron goes to the right of the circle. Then you draw the outer shell of the atom with the highest group number as a pair of crosses, with the unpaired electron go this time to the left of the circle. So here we have the example here. So hydrogen, okay, is of course in group 1, so it's going to go on the left, and the unpaired electron goes on the right of the circle as a dot. And then we have chlorine, which of course is in group 7, okay, so it's going to have all its paired up electrons in the circle, and the only one which is not unpaired, or which is unpaired, goes to the left of the circle. So what are the properties of these simple covalent molecules? So they have low melting points and boiling points. This is because of the weak intermolecular forces which are easy to break down. Now, what's an intermolecular force? That's a very good question. Okay, so an intermolecular force is going to be the force between molecules. Okay, international, between countries, intermolecular, between molecules. Okay, so for example, like hydrogen chloride, okay, there will be a weak force between the hydrogen chloride molecules. Okay, that is known as a intermolecular force. Okay, and they're quite weak and reasonably easy to break compared to the covalent bond, which is very, very strong. Okay, so this actually gives some of the properties of simple covalent molecules. Okay, they are also non-conductive. They don't conduct because they have no free electrons or the charges are unable to move, as opposed to ionic bonding, where if you dissolved or melted an ionic salt, they'd be able to conduct because the charges couldn't move. Hydrogen, ammonia, methane, and water are also simple molecules with covalent bonds. Okay, so hydrogen, ammonia, methane, and water do not conduct electricity, and they have reasonably low melting points and boiling points. And that's just an animation illustrating what intermolecular forces are. Okay, the intermolecular forces are these ones here, the forces between the molecules, and then we have the intramolecular forces, which are the covalent bonds, which are very, very strong. Okay, there we go. So the intermolecular forces are rather weak, whereas the intramolecular covalent bonds are relatively strong. So when one of these substances melts or boils, it is these weak intermolecular forces that break, not the stronger covalent bonds. An important point to note. So simple molecular substances like water are gases, liquids, or solids with low melting or boiling points. And this is the reason why. Also, it's important to consider the molecular mass and the melting and boiling points, which can be shown in the graph. Okay, so fluorine has the lowest molecular mass and iodine has the highest. So you should expect fluorine to have a lower boiling point than iodine. And the reason why is that you have increased intermolecular bonding in a bigger molecule. So there'll be more bonds, these intermolecular bonds that need to be broken. Therefore, the greater the molecular mass, the higher the melting or boiling point of that particular substance. So that was simple covalent molecular compounds like water and ammonia. We're now going to look at the more complex giant covalent structures. Okay, so giant covalent structures contain a lot of the non-metal atoms, each joined to the adjacent atoms by covalent bonds, which you can see in the diagrams. The atoms are arranged in regular lattices, just like in ionic bonding, and they're extremely strong because there's many bonds involved. The pictures show the molecular structure of diamond, graphite, and also silicon dioxide, which are giant covalent structures, and diamond and graphite are two allotropes of carbon. Okay, so that means that they are carbon, but they're in different structural forms. Okay, this guy here, graphite, okay, and this guy is diamond. And they have special properties. So in terms of these giant covalent network solids, this is important. You have to be able to compare and contrast them. And the reasoning why, they have slightly different properties. So graphite is a form of carbon in which the atoms form layers. As you can see here, you've got 1, 2, 3 layers. These layers can slide over each other, okay, so they can move back and forth, okay. So that means that they can act as a lubricant, and it is also the fact that graphite is a lot softer than diamond. Graphite's pretty much what your pencil's made of. Each carbon atom is a layer joined to only 3 carbons, okay, rather than 4, and because of this, graphite can also conduct electricity because it has a free electron. Diamond, on the other hand, is a form of carbon in which every carbon is joined to another carbon. Okay, it has maximum 4 bonds. As a result, there's lots and lots of bonds to break. It is very hard, and because it takes lots of energy to break these 4 bonds, it has a high melting point. And it does not have a free electron. So because it doesn't have a free electron, it does not conduct electricity. And silica, the last one, which contains silicon and oxygen bonds, has a similar structure to diamond. It is also hard and also has a high melting point, but instead of containing carbon only, it contains both silicon and oxygen atoms. So finally, what are the properties of the covalent network solids, which we just briefly looked at? Well, they have very high melting points because they have lots of strong covalent bonds that must be broken. That requires energy. Okay, there's the example there comparing the structure of graphite and diamond. 4 covalent bonds in diamond. Okay, it's got 4, and graphite only has 3, so it's slightly lower melting point. But you've also got weak intermolecular forces between the layers, and also because it has a free electron, graphite can conduct electricity. Okay, diamond does not conduct electricity because it doesn't have a free electron, whereas graphite contains free electrons, therefore it conducts electricity. And finally, silicon is semiconductive, so it's between being conductive and non-conductive. And that is pretty much, in a nutshell, covalent bonding for this unit.
Hello everyone, Mr. Kazi here with another lesson in chemistry, and today we're going to talk about chemical bonds. I know you're all excited about that. So let's get started here and see what we have in store today. In order to understand chemical bonds, you must know some things. So we want to make sure that we understand the 2 basic rules of physics: valence electrons, Lewis dot symbols, the octet rule, oxidation numbers, and electronegativity. And we need to have these things down in order to understand chemical bonds. Now, the other thing here is, before we get started, make sure you have a periodic table. If you don't have a periodic table in front of you right now, you're not prepared to succeed. Get your periodic table and get ready to learn about chemical bonds. The 2 basic rules of physics are this: opposites attract and likes repel, and nature moves in the direction of least resistance, which means nature moves towards the lowest energy. We have these 2 ideas down in order to work with the octet rule. All right, valence electrons, the electrons in the highest energy level, and it's usually the S and P's. Electronegativity is the measure of an atom's ability to attract electrons to itself. And it increases as you go across, and it increases as you go up. Now remember, that doesn't include the noble gases. The noble gases right here, electronegativity is 0. They don't want to attract electrons. They don't want to give up electrons. They are good the way they are. They have their full octet or duet. What is chemical bonding? Chemical bonding is the process by which elements combine to form a compound. And a chemical bond is the electrostatic attractive forces between atoms strong enough for the atoms to act as a single unit. This attraction is created by the transferring or sharing of electrons. Now remember, in past lessons we've talked about electrons being the most important thing that we wanted to learn about the atomic model. And the reason we wanted to know about electrons is that it's electrons that determine the valence shells, and it's the electrons that determine the chemical bonding. And how elements come together and bond and form compounds is all dealing with the electron. We need to know about the electrons' ability to attract each other, and it's this transferring or sharing of electrons that's going to make the difference. And usually this involves the valence electrons. 2 major chemical bonds. There's the ionic bond and the covalent bond. Those are the 2 major chemical bonds, and we need to learn about them. So the ionic bonds are created by the transferring of electrons. One atom gives up its electron to the other atom. Boom. And usually it's between a metal and a nonmetal, and they create ionic compounds. Example, there's sodium and chlorine, and you'll notice here that sodium wants to lose and chlorine wants to gain. That's perfect. So sodium is going to give up its electron, and so the electron is transferred to chlorine, and when that happens we create 2 ions. As soon as the sodium gave up its electron, it got a positive charge, and then chlorine accepted that transfer, and chlorine got a negative charge. And what happens to opposite charges? They attract. And so now we have that strong ionic bond created by the attraction between sodium ion and the chlorine ion. Covalent bonds are created by the sharing of electrons. Now, it's not so much a transfer of electrons, but a sharing of the electrons between two atoms. It's between a nonmetal and a nonmetal, and of course they create covalent compounds. Here's an example. We have some hydrogen and some oxygen. Now notice oxygen wants 2 electrons. And so we had to have 2 hydrogens. But by sharing electrons, that gives hydrogen its duet, and it gives oxygen its octet. So everybody's happy. Okay, now let's look at some examples here. What bond will form? Sodium and iodine together. So what bond is that? Hopefully you said ionic. Hydrogen and oxygen coming together. We kind of already did this one, and it's covalent. Here's a lithium and fluorine. When they come together, ionic. How about carbon and neon? Neither. Why? Well, there's no bond because neon is a noble gas. The octet's full. It doesn't want a bond. It doesn't need electrons. Doesn't want to give up electrons. Then we have sulfur and fluorine, covalent. And arsenic and chlorine, covalent and somewhat ionic. Now it's a semi-metal and chlorine. Chlorine's very electronegative. And so I would say it's probably mostly or predominantly covalent. But you're going to see some ionic property in it because arsenic being a semi-metal and can act like a metal or a non-metal. So on that one, a little bit tougher, but still doable. And you can check that with electronegativities and determine whether or not you want to call it covalent or ionic. Note, ionic and covalent represent extremes. Most bonds are somewhere in between, where they're somewhat ionic and somewhat covalent. And what we look for is it mostly covalent or is it mostly ionic? And a lot of that can be determined by their electronegativities. You know, ionic is a metal and a nonmetal, and covalent is a nonmetal and a nonmetal. It's a good rule of thumb to help you determine the bonds that you're looking at. Let's look at compound characteristics. Ionic compounds are between a metal and a nonmetal, have high melting points, they have high boiling points, are crystalline solids. And as far as I know, they're all crystalline solids. The ionic bond is so strong that they're all crystalline solids, are good conductors of electricity, and most are soluble in water. Water, being very polar, attracts ionic compounds, and most ionic compounds dissolve in water. Covalent compounds are between a nonmetal and a nonmetal, have low melting points, have high boiling points, can be gas, liquid, or solid, depending on what's bonding and how strong that attraction is going to be, are poor conductors of electricity, and as a whole, most are not soluble in water. Even though some covalent compounds are soluble in water, water is very polar. Remember, water is the universal solvent, and because water is polar, which we'll be talking about in a later lesson, it can dissolve more things than any other substance. But still, we consider most covalent compounds to be not soluble, especially your organic covalent compounds. All right, let's play Name That Bond. Da, 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 da. What is the main bond? In lithium chloride, ionic. Carbon dioxide, covalent. Ammonia, and that's called ammonia, not nitrogen trihydride. That's ammonia, covalent. Calcium fluoride, ionic. Metal and a non-metal. Magnesium phosphide, ionic. CH4, methane, organic compound, covalent. And SF2, covalent. All right. Why is calcium fluoride ionic? Let's go over and check it out. Why is CH4? Well, let's look at it. Covalent? Why? Here you go. Pretty self-explanatory. Thinking time. Predict the formula of a compound composed of aluminum and chlorine. First, decide if the elements will bond. Well, that's a positive and a negative, and we know opposites attract, so of course it'll bond. If yes, then determine the charges and bonds. Well, we already did that. 3 bonds, 1 bond. Just need 3 chlorines to make it work. If you have any questions, send an email to Mr. Causey at mrcausey.com, and check out www.mrcausey.com. PowerPoint videos and much, much more. A lot of notes there. And if you have any requests, you can go there and use the contact form and get a hold of me and ask for a lesson that you might like me to put together. And happy ions!